All right, welcome back, everyone. This is the final lecture of Anne-Marie.
So, thank you, Haluk. So first, I would like to thank the organizer for this very nice summer school and all the other three speakers for their wonderful talks. So I learned a lot from them, sorry, and I hope everybody does. So now I arrive to my third lecture. So I will try to, first thing, I will give an example of a bad fixed point. So this is a remind to the talk of yesterday. So first I recall what we call the good fixed point. So just to remind you, big theta was the inertial class of a pair formed by a Levy subgroup M and a square integrable mode center representation of M omega, and you said that and omega is a fixed point under the action. We assume that omega is a fixed point under the action of W theta, which is the fixator of theta, and we said that omega is good if for every point in the orbit of omega under the action of a group of unitarily unramified character of M, the decomposition of W tau and the decomposition of W omega are compatible in the following sense, so which is recalled here. So the Val group attached to omega is the biggest one. It contains all the other Val group of the representation in the orbit, and something quite similar for the R group, but a bit weaker. So with the R group of any other element in the orbit is isomorphic with a subgroup of the R group of omega. So here is an example. So it's very easy to find a bad fixed point, actually. And they occur, especially in particular in the case where the representation, in the case of principal series. So we will take omega a trivial character. So we just give it in the case of SL2F. You can make a similar example for example, symplectic group. So we take a trivial character of a diagonal torus T of SL2, which is isomorphic with F cross. Then this point is a fixed point. I mean, this is clear because it's the trivial character, so it's fixed by everything. And but it is not good. And so if you look at the group W theta, in this case it is a Y group, so we just have the Y part of it. So R omega is trivial. So W omega is W theta because it's W omega and it is W prime omega, and here it is Z mod 2. And then you can consider the character, the unique unramified character of F cross, which was denoted before by sign epsilon, view as a character of T. And then if you compute the R group of R epsilon, so omega is trivial, this R group is Z mod 2. So it is not isomorphic to a subgroup of R omega. And of course, this example shows that the situation is even worse. There is no good fixed point in this case for the pair theta, or this pair theta. So in fact, if you take any character, unitarily unramified character of a torus, then if you tend, so omega is just a trivial character, but omega tensor by chi cannot be at the same time a fixed point and a good one. So because it has, if you request that it is a fixed point, you find that it has to chi has to be of order 2. So chi is a unitarily unramified character. So chi, the only possibility for chi are 1 or epsilon, and in both cases, we have the R group, which is 1. And so if you repeat the same argument as above, but changing to a trivial character into epsilon, we also get that epsilon cannot be a good fixed point. Okay, so it's just to say that the example where we are not in this situation, and at the moment we do not know what should be the result in that case, and actually it's not clear how to formulate it. Okay, so it's something to think about. But now for today, I will talk about another direction which might help to understand this question too, which is the case of, I will come back to smooth representations, and we'll try to explain to you how we can view you can decompose the category of smooth representation of G into blocks. So this is due to Bernstein, and for that we'll need the following notions. So these notions are very parallel to the one we have yesterday regarding square integrable and their orbit under unitarily ramified character. The only difference here is that we are looking at supercuspidal representation instead of discrete series, and any ramified character, not only the unitary ones. So now I will fix L a Levy subgroup of a parabolic subgroup of G. So a character is, as I already said, is called unramified if it is trivial on every compact subgroup of a Levy, and you will denote by X and R of L the group of unramified characters of L. So now let sigma be an irreducible supercuspidal smooth representation of L, and denote by O the orbit of sigma under that group of unramified character psi NRL. And so it's very parallel to what we have yesterday. It said that now omega is replaced by sigma, and the relation, the equivalence relation, allowed to twist by any unramified character. So I will denote sometimes, so S will be the G conjugacy class of a pair LO, and if sometimes I will need to fix, to be easier to fix a base point, and in that case I will write it as L sigma bracket G. We will denote, we consider the set of such classes L, and we will denote this set as B of G. And in the particular case where we want to consider such a conjugacy class, but in the Levy, so LO, so the conjugation is inside L, I will denote it by S sub L. So these are just notation. Sorry. Now, so let R of G be the category of all smooth complex representation of G. Then this, so Bernstein described decomposition of this category as a direct product of subcategory. And so the subcategory are defined as follows. So one category for each element S. So Rs of G is defined to be the subcategory of Rg, whose objects are the representation pi v, which are the property that every subquotient of pi is equivalent to a subquotient of a parabolically induced representation. So in my presentation, it should be I L pi, so L prime P G of sigma prime, where sigma prime is in the orbit of sigma under the group of unramified character of L. Okay, I will, and then we will denote by Ir S of G the set of irreducible objects in that subcategory. So this subcategory are indecomposable and split the full subcategory R of G in a dialogue product. So this is a very important and very useful result, because it's allow us to in order to understand the category, to fix one S and to look at this subcategory RS. And so this is interesting because this subcategory have interesting property and a very rich structure that we will try to explain later. So now our first, state a remark. So this is at the Bernstein decomposition is at the level of category, but of course we can consider the irreducible object in all these categories, and you get a decomposition of the smooth dual of G, which we denoted by E of G, as a product of some blocks. The product is all the inertial classes S in B of G. And this block for fixed S, the corresponding block here S of G, is just by definition, it is contain all the representation which correspond to S by parabolic induction, as we have explained before. And I will denote by new sub B I will call it the inertial supercuspidal map. So it's a supercuspidal support map. So it's the map which sends any irreducible representation to the block attached to it. Okay, so this stopped for the Bernstein decomposition, but the previous days we were interested in Champer representation. So we could consider the intersection of these two decompositions. So if you fix S and you in the block RS. So I will set for the category of block, and for this just a series, so for irreducible representation. So we consider the series attached to S, and inside this series we look at all the representations that are tempered. And it is a product of the series, tempered series that we have seen before, here T theta of G for all the theta, but that the property that the map Z, which is the supercuspidal map for theta, send theta into the Bernstein component S. So this will be interesting, hopefully, because it will relate the Bernstein decomposition with tempered world. Okay, so now I come again to the Bernstein decomposition in general. So I will fix S an element in B of G, and so L is a Lewis subgroup of G. And we will consider the intersection of a kernel of all the unramified character of L, and denoted this as L1. So E will denote a space for the supercuspidal representation sigma of L. And so, of course, L1 is contained in L, and you can consider the restriction of sigma to L1, and you will. And that restriction is semi-simple, but is not irreducible in general. And so we will call sigma 1, we will pick sigma 1 E1 an irreducible component of a restriction of sigma to L1. And we will consider the functor of compact induction that we have introduced in the first talk from L1 to L. So this is interesting because first, if you just consider the induction of sigma 1 from L1 to L, you get a representation which does not depend on the choice of sigma 1. So if you have taken another irreducible component of the restriction of sigma, you will get the same representation up to isomorphism. And this element that I will denote by pi LSL is a progenerator of a category RSLL. And then if you induce parabolically so now we have used compact induction, and now from L to G we are using parabolic induction, and you will induce that representation pi L SLL from L to G parabolically, and what you get is of course an element, an object of a category RS of G, but it is a progenerator of a category. And so this is interesting. So this is due to Bernstein, and we can find proofs in a paper by Alan Roche in I think in composition, if I'm correct. So this is useful for the following reason. Now we can consider, if you have a progenerator in the category, you can consider the functor which send a representation to the G homomorphism of that progenitor with value in V. And this defines an equivalence from RS of G to the endomorphism algebra of your progenerator. So if you come back to the general picture, so you have the category of smooth representation of G, R of G. You obtain, I think Bernstein give us a decomposition of that category into blocks, and for each blocks we can view the block as up to equivalence as the endomorphism algebra of a certain progenerator. And it is expected that this endomorphism algebra has a nice structure. Okay, so maybe some word about it, because we have recent progress are made recently. So first, a few years ago, when in the case where G is either an inner form of GLN over F or classical groups, then Volker Heiermann has studied this endomorphism algebra and show that it is an extended affine Hecke algebra. And quite recently, Martin Solovel studied this in general, and the result is that this endomorphism algebra is a twisted, extended affine Hecke algebra. So, and if you consider, if you assume that the restriction, if you assume that the restriction of your representation sigma to L1 is as always multiplicity 1, so it's not necessarily irreducible, but all the representation are on the component are non-equivalent. In that case, so Sullivan has more precise result, and in particular is able to show that it's inside this this endomorphism algebra we have an affine Hecke algebra. Okay, and this condition is very often satisfied. For instance, if Levy is a product of a group like GLN group, this is satisfied. But it's not. I mean, okay. So we get this. So it's one thing. But I will emphasize the fact that this algebra has to be in general is twisted, and especially so the way as the R group in this situation acts might be difficult to understand. And in particular, already several years ago, it was studied in the case of SLN by Goldberg and Roche, and they show that this endomorphism algebra is not, in general, a affine ecoalgebra, even extended. So it is, but up to some scalar. And the method that was used by Goldberg and Roche was the theory of types. So it will be what we are going to briefly review now. For that, you will first consider the algebra H of G, which is the space of locally constant, compactly supported function from G to C. And you can view this algebra as a C algebra by using the convolution relative to a fixed R measure. So this is well known. And now we will consider an open compact subgroup K of G and rho a smooth representation of K with contragradient denoted as tilde rho. Then we can define certain algebra, so attached to rho. This algebra Hg of rho is defined as the space of compactly supported function from G with value in the endomorphism of the vector space of rho tilde. And we want that this representation are rho tilde spherical, which means that if you compute the value, if you evaluate f at at kgk prime, you get this formula, so rho tilde k f of g rho tilde of k prime. So this is a generalization of a k spherical algebra in the case when you take rho just a trivial representation. So this, again, the convolution product equips this algebra with the structure of a unitarily associative C algebra. And you can define and attach to it an idempotent, which is the function defined as follows. So for the element which are not in K, 0, and for the element in K, if G is in K, you consider essentially the trace of G at G minus 1 with normalizing factor. And so this element E sub rho is an idempotent, so its square is equal to itself. And you can consider the corner algebra associated to this idempotent. So it is the algebra E sub rho star AG star E sub rho, where star is a convolution. And this one is a subalgebra of H of G with unit E sub rho. So the big algebra H does not have a unit in general. So now we are a smaller algebra, and you can consider you can view it. So you have two algebra. Sorry, this one, the corner algebra, and the algebra attached to K rho. So the relation between these two is the following, which was studied by Bushnell and Katsko. So we have a canonical isomorphism from the tensor product of the first one with the endomorphism, C endomorphism of 0 and the second algebra. So in particular, these two algebra are canonically Morita equivalent. And so we get an equivalence, a canonical equivalence of category between their modules category. Okay, so now we have this. You will introduce the following notation. You will denote by R sub rho the full subcategory of R of G, whose objects are those representations that satisfy with space V satisfied by the V is H G star hero star V. In other words, it is the full subcategory generated over G by the subspace E rho star V. So now we have a full subcategory of RG, and by Bernstein we also have seen before that we have a decomposition of RG. So the goal will be to relate these two directions, and this is done using the notion of types of S type, which is due to Bushnell and Cusco, and the definition is the following. So, so we start with a pair. So I don't know. K rho. It is called an S type if the category, this subcategory R rho of G is closed by subquotient, and an equivalent characterization of an S type. So an equivalent definition is the following. First, an example, sorry. If you take for K just the Iwori subgroup, an Iwori subgroup of G, and for rho the trivial representation. So so by an Iwori subgroup, for instance, if you take GLN, you will consider inside GLN over F, you can consider GLN over the ring of integers over OF, and you can, there is a natural reduction map from GLN OF to GLN over KF, where KF is the residual field of F. And so so what you get is GLN over KF, so it's a finite group of Lie types, and you can consider a Borel subgroup in it. So for GLN, it's just the, for instance, the up diagonal triangular matrices, and you consider the inverse image of that Borel subgroup under the reduction map, and what you get is a subgroup of GLNO, and this is an example of standard Iwori subgroup in GLNO. So now come back to my example. So we have a pair, an Iwori subgroup and the trivial representation of it. And then it is an S, an S type. Okay, sorry, something is wrong in my notation here. So it's an S type for the pair T, comma, some character, and here it's just the trivial character. There's no S here. So which means that you take the trivial, we take the torus, which is associated to the Iwori subgroup. So in the case of, again, in my example of GLN, it would be just the diagonal torus, and you take the trivial representation of that torus, or any unramified character, which is because of, here you have the orbit of by the unramified character. So this is the first example, and in some sense it is a prototype of type, and this example was studied in detail by Borel in long time ago in a paper, which is something admissible representation for semi-simple groups, and he has the decomposition of a category in that case. And it's the paper which inspired the notion of types. So now, so the characterization of a type is the following. So it's a pair K rho is an S type for G, if and only if the following the condition is satisfied. So the restriction of pi to K contains rho if and only if the inertial support of inertial supercuspidal support of pi belongs to our inertial class S. Okay, so it should be an if and an if, yeah. And in fact, in many cases, this characterization which would be useful. There is it's possible to consider some weaker notion. which is something like alpha type. And it is a notion of typical representation. So a typical representation is you start again with K rho, and it is S typical if we have a representation pi such that its restriction contains rho, then it implies that the inertial support of pi is in your S, the inertial class S. So I will not talk about S typical, and of course the type is S typical, and I will not talk about S typical today, but I think it's an interesting direction, and so it's so in the case of GL2, it was first considered by Enya in the case of GL2 in an appendix of a paper of Breuil and Mezar on long-length correspondence for mod P long-length correspondence. And it's interesting because it's allowed to relax the condition, and I think it has some relation with, it should have some relation with temporal representations, more precise. Okay, so now come back to an S type, and the main result of Bushnell and Cusco for an arbitrary PID group is the following: that the category, and this is the reason for introducing the notion of S type. If K rho is an S type, then the category R rho of G coincide with the category RS of G. And in particular, the latter is equivalent to a category of module on this algebra. So it means that in order to understand this category RS of G, you have two ways. So using Bernstein progenerator or using the theory of type. And so it's using this, you also can define a progenerator. And this theory, I mean, give the same, essentially the same result in the case where the type has nice property, and in particular so we like to construct S type, and the way to do that, which is starting by constructing an S type for any Levy, an SL type for any Levy subgroup L of G, and then from that, for an SL type over the Levy, there is a general procedure due to Bushnell and Casco to induce the type in some sense, which is the notion of G cover of a type, and then the algebra. The algebra will be the algebra of this G cover, and and to study is computed explicitly. Okay, a few words about what is the situation at the moment. So if P is large enough, which means P is the residual characteristic of our p-adic field. So if P is large enough, which means that P does not divide the order of a Y group of G, then S type have been constructed for any group G, which is any unramified group G. So as I already said before, you constructed in this situation all the supercuspidal representation for G and also for its Levy subgroup, and Kim and you use this, define and extended this U construction to non-supercuspidal representation, and the type that they obtain are covers of types constructed by you on the Levy. So this means, and so this is in general, but P is assumed to be large, and if P for classical group, it's also known when P is odd by the work of Sean Stevens for supercuspidal and Miyaoshi Stevens to pass from supercuspidal to non-supercuspidal situation. For GLN and its inner form, and for SLN, the theory of type is known for every group, with no condition on P and no condition on F. And the equialgebra are computed, so we know what are the equialgebra algebra. Now, if you look at inner form of GLN, thanks to the work of Broussus, Secher, and Stevens, we also have a construction in all the cases of the types and of the equialgebras. But then, if you look at SL and the inner form of SLN for SL2, it is now known by a very different construction, thanks to quite recent work of Weissman. And but when n is greater than 2, it's still open. So we do not have a type, and of course we do not. We do not have a types. Okay. And actually, we have some equialgebras which we constructed with Baum, Plyman, and Solovel. But these algebras are not attached to a type in SLN. Of course, we do not have a type. But we can embed the SLN in GLN, and similarly for the inner form, and the equialgebra we have constructed are in fact attached to a restriction of from GLN, or in fact, from GLN to SLN. And so this seems to be something that's not exactly the theory of type, but quite recently, my former student, Pei Kui, has obtained a similar result for mod L representation of SLN. So she obtained a block decomposition of the category in this situation. So this is something I would like to mention, that the Bernstein decomposition does not work for L modular representation. So we do not have a block decomposition. So there are many things to say for L modular representation or P modular ones, but I do not have time to go in that direction today. So now for the last part of the talk, I will try to link the theory of Bernstein decomposition to K-theory and non-commutative geometry. And for this, I will need the following notions. So first, I am a Levy subgroup, and I consider the stabilizer of sigma under the group of unramified character, which is what I denote by X and RL sigma. And we can consider, of course, it is contained in the group of unramified character. You can consider the quotient, and so there is a bijection. I mean, it's clearly a bijection from this quotient to the irreducible object in the category R SL of L. We just send a character chi to the twist of sigma with chi. And this endows this IR SLL with a structure of a complex tolus. And up to isomorphism, this tolus depends only on S. So it's only up to isomorphism because as you see, to define this tolus, we have fixed sigma. So it means that we have chosen a base point in S. But up to isomorphism, this tolus does not depend on the choice of a base point. So it depends only on S. And it is known as the Bernstein tolus. So this construction is due to Bernstein. And and also, so it is, so I can repeat in what I say in a different word. So TS is only an algebraic complex variety, and there is no natural multiplication map on it. But anyway, it's very nice to have this algebraic variety, and it will, and also Bernstein has introduced another group. So we can consider the normalizer. So this is very similar to what we have yesterday regarding the decomposition of, regarding the group attached to discrete series, by group attached to discrete series. So it's similar. Here you consider the normalizer of L mod L. And in that group, you consider the element which send our representation. Okay, sorry, this row should be sigma. We send sigma to a twist of sigma by some unramified character of it. So it's exactly the same definition as the group, similar definition as W theta of yesterday, except that here we allow to twist by any unramified character, not only the unitary ones. So this group is an extended Weil group. By extended Weil group, I mean that it is a semi-direct product of a finite Weil group by some R group, which is the same as defined in, which is it's similar to Knapp-Stein decomposition here. So this R group is the set of elements in DWS which send positive root to positive root. And this group acts naturally on our group TS by automorphism of algebraic variety. Okay, one more comment about the category. We can look at the category center, which means the endomorphism, yes, which is the endomorphism factor of the identity, the commuting. Okay, and if we do that, you get. Okay, my notation are not good. This means this O is not the orbit, but it is the coordinate algebra of TS, fixed point by DWS, which can be also viewed as the coordinate algebra of a quotient of TS by DWS. So this, so we see that this quotient has some importance here, and this coordinate algebra is also, by construction, the center of the endomorphism algebra of a progenerator we have seen before. So now we have, so this leads me to introduce the notion of so this is a quotient, this was a quotient of extended quotient, so which was due to Bauman code, and which is the following. So we have a finite group. So in my case, it will be the group WS acting on a complex affine variety. So we will apply it to TS. And so first we can consider the isotropic group subgroup of X, so the element of gamma which fix X. And okay, I will also denote it's by, okay, this notation is imported from Lustig papers. So underline of gamma X would be the set of conjugacy classes of gamma sub X, and here of gamma X is the set of equivalence classes of irreducible representation of gamma X. And we can attach to gamma and X to the following two sets. So X tilde geo, which for geometric, which is the set of pairs X gamma X underline gamma, such that okay, it should be underlined here. Should be an underline under gamma, such that underline of gamma is in gamma is a conjugacy class of gamma X, and the spectral version, which is defined as follows. So today we will use the geometrical version, but for later purpose, for instance, in relation with local long loss correspondence, is the spectral version, which is more useful. Okay, and then we have an action of our group gamma on both these sets as naturally action as follows. And so we can consider the quotient of this set of this set, for instance, of x theta geo by the action of gamma, and similarly for the other one. And we call this quotient the extended quotient of x by gamma, so geometric extended quotient for the one on the left and spectral extended quotient for the one on the right. So just a little, I mean, it's kind of rephrasing what the definition. So when you consider the ordinary quotient, so x mod gamma, we collapse each orbit to a point, and the geometric extended quotient is obtained by replacing the orbit of x by this group gamma sub x, this set of element. And for the spectral quotient is similar, but in that case you replace the orbit of x by the set of irreducible representation of the isotropic group gamma x. Okay, clearly these two sets are in bijection, but the point is that in general they are not, there is no canonical bijection between them. And as a consequence, the two versions of the extended quotient are in bijection, but again, not in a canonical way in general. And of course, by definition, we have a natural projection from the extended quotient, from each extended quotient to the usual quotient x mod gamma. Okay, so now we will apply this soon. So first thing, we have a decomposition, density decomposition. This decomposition implies a decomposition of a reduced C-star algebra of G, which will be useful for us. So the decomposition is like this. And so if you, a way to write it is, as I tried to explain yesterday, the C-star algebra is related to the tempered dual of G, and we define this as, we view this as the intersection of a representation in the tempered dual, which corresponds to the block, the Bernstein series attached to S. Okay, today in the world of smooth representation, we were considering the orbit of sigma. So sigma is a supercuspidal representation. We were considering the orbit of sigma by the group of unramified characters of L. But of course, we can consider a smaller orbit in which you just consider the action by the group of unitarily unramified characters of L. So now I am trying to mix so sigma, the two situations. So I will take sigma unit and take in sigma unitary. Then you can consider. Then in that case, you can state the following conjecture. So we look at the K theory, the usual K theory of not on. So in Baum-Cohn, you consider the K theory of a C-star algebra. So here we are looking at the K theory of a given block of a C-star algebra attached to S. And we expect that this K theory is isomorphic with KJWS of that of TSU. So where KJWS is the classical topological equivalent K theory for the Lie group, the extended Lie group DWS acting on the compact torus TSU. So this one is contained in TS, and TS can be viewed as a torus, and TSU is the compact torus in TS. Okay, so in some sense, it can be viewed as a close to BAM conjecture, but block by blocks. Okay, sorry. And so a few words about this. So we can look at this conjecture in a special case when the group is split and when the benzene component S is the E1, which means that I will take I will replace here S by I, and I will take for the Levy L the maximal split torus in G, and for the representation sigma, just the trivial representation of that torus. So in that case, so the group WS, because the representation is trivial, it's just the normalizer in G of T mod T, which means that it is just a Y group of G with respect to T, but I will denote it just simply by W. And TUE is a maximal torus in, it's the maximal compact subgroup of T. But this T can be viewed as a maximal torus, in the long-length dual group G check of G, which is a complex Lie group with root system dual to that of G. For instance, if G is GLN over F, G check is GLN over C, and if G is SLN over F, G check would be PGLN over C. Okay, and now I just rewrite the conjecture, so it's exactly the same word, except that I change S into I. So it is exactly the same, but I replace S with I and WS by all the group, the entire group W. And then it's possible to prove, so we can prove this result, the analogous result, the weaker form up to torsion. And if we do that, then you can apply the chain character on this part, and we obtain modulo torsion, that the total cohomology, even when G is 0 and odd when G is 1, of the geometric extended quotient of the compact torus by W. So here we see that what show up is an extended quotient again, but where instead of taking taking the usual torus, we just take a compact torus. So this is the special case, but we can look again at the conjecture. And another interesting case that so it would be, I guess it would be nice to be able to understand the link between this and the decomposition, the Stein decomposition, and the description up to Morita equivalence that we have of this block of a Caesar algebra that we have seen yesterday, but it was not exactly the same block. It was a block C star R G theta, and theta was an inertial class attached to a discrete series, and it was inertial class by twisting only by unitary character, ununified character. So, but there is a kind of, as Hocher, Kleiman and emphasis recently, we can look at a special case in which your representation omega is in fact unitary supercuspidal representation, and then you can try to compare what we get in the case of a good fixed point data and this statement and seeing how they are related. So I will arrive at the end of my talk, but I would like to just give some reference of some direction that I didn't get time to explore in this lecture. So the first direction is, in some sense, the cycle of what we are just talking about. So trying to relate the notion of Bernstein decomposition or the notion of type theory in the case of temporal representation. So in the case of GLN, it was done a long time ago by Schneider and Zink in this paper. And so it's quite interesting in the sense that they constructed types, but a different notion of types, which is attached to tempered component of the category. And more recently, the Schneider and Zink also have studied in a general situation the temporal representation for periodic group. And clearly there are many things which should be interesting to look at. So this is a direction. And different direction is until now, so we have only seen one case, which, so we have seen the case of Iwori representation with Iwori fixed vectors. And, but this is a very special case. We have more situation when you replace, for instance, the Iwori subgroup by a more general group, a paraoric subgroup. And instead of taking just the trivial representation, you take a paraoric subgroup. It has a reductive quotient, which is a finite group over, which is a Lie group of finite D group over the residue field, so a group defined over the residue field, and you can inflate a cuspidal representation of that group to get representation of G, and doing that you will get the representation which are said to be of depth 0. Okay, so this is one direction, but if you want to consider representation which are not depth 0, there are, I would say, two ways of doing that. One way is to use the theory of types. And a slightly different way is to, instead of considering just the residue field, is to consider finite rings which are just obtained by OF mod a power pi f r of integral power of maximal ideal of OF. And so we all have to group like G over a finite ring, an algebraic reductive group, the point of such a group on a finite ring. And for example, we can take for this group GLN or SLN. But this is the situation of the way of studying representation theory for this group is much more difficult. Actually, it is a wide problem. But anyway, there are some results in that direction. The first one, which should be in my list here, is the paper by Lustig in Corvallis, which is also about SL2, and more recent paper by Lustig in that direction. And very recently, there was also a very interesting work by Chris, Meyer, and Owen, in which we define a new version of induction, so which is called a variant of Arishona functors, which, and also works of Stasinski on several work of Stasinski on representation of periodic groups over finite local rings, and in particular this recent paper in the case of SLN. And also, so the relation between this theory and the theory of type is not easy to deal with. So there are some results by Stasinski and Stevens And also the paper in the case of GLP, where P is prime over OF by my former student, Anna Tsumovic. And related by rather different direction is to consider the restriction of the representation of a group to study its restriction to a maximal compact subgroup. And so this arrived to the world of branching rules. And so I want, for instance, this work by Monica Nevens in the case of supercuspidal of SL2, and also several recent work of several people for in the case of typical representation, and this are also related to this question. So I will stop now. Thank you very much for your attention.
Thank you, Anne-Marie. Okay, I've got 2 questions
Yes.
from the chat box. One is says that I often read that an unramified character or representation is one having fixed vectors for a hyperspecial compact subgroup when it exists. Here we are requiring the character to be trivial on all compacts as opposed to hyperspecial compacts. Is that equivalent, or if not, what's the relationship?
Okay, it's an interesting question. Okay, of course, the condition I gave is stronger, I think, again. And okay, first, we do not have always hyperspecial maximal compact, but if a group is split, it would be okay. Okay.
So if they exist, it's certainly weaker condition. So they're not equivalent, right? Just requiring fixed vectors for hyperspecial compact subgroups wouldn't imply on all compacts.
Okay, I do not know, but I would guess that it is weaker.
Okay. Another question is about the categorical equivalence of RSG and the endomorphism, G-endomorphism algebra. Is it possible to revisit that equivalence? It wasn't the question, was it, do we want the module, so category of modules over that endomorphism algebra on the other side, or? It was as a corollary of a theorem on constructing progenerators.
Yes, it's this one, yeah.
Yes.
And what is so the question is about if
it's an equivalence on the category of modules over the endomorphism algebra, or is that the question, or is this, how does it work?
Yes, it will give an equivalence of module of the endomorphism algebra. Yeah.
Okay. So it's yeah. So but that was the question. So it's on the module on the algebra. Okay, these are the 2 lingering questions from the lecture. Any other questions or comments to Anne-Marie? Lecture?
Yes, I'd just like to illustrate our conjecture with an example. So suppose the conjecture right at the end, right. Now, the simplest possible situation is when that little s is such as to produce the spherical principal series for SL2. The spherical principal series for SL2. Everything unitary. So here, from a topological point of view, you get a unit interval with a double point at one end and an isolated point, the Steinberg representation. So that's a compact non-Hausdorff space. And when you look into its K theory, K0 has three generators. So K0 is Z plus Z plus Z. But on the other side, you have to look at the equivariant K theory of the circle, where the equivariance is with respect to the two-element group. So what are we talking about? We're talking about Z2 bundles on the circle. Now, there are not very many of them. I think basically what you're left with is the trivial complex line bundle on the circle. But there are three ways of giving that the structure of a Z2 bundle. You can either let Z2 act trivially on the fiber and the base, or you can let Z2 act just on the base, or you can let Z2 act on the fiber and the base simultaneously. In the fiber, you'd send Z to minus Z, and in the base, you'd send Z to the inverse of Z. And I think when you do that, you exhaust the equivariant K theory of the circle. So there are three Z2 line bundles which create distinct elements in the K theory. But the whole point of this conjecture is that we're relating incredibly different things. So you see what I'm talking about? So you have that subspace of the tempered dual on the left-hand side with that double point and the Steinberg representation on the left-hand side, but on the right-hand side, you have this very, very elementary, these very elementary items, complex line bundles on the circle with three different actions of Z2. And these two things are in one correspondence to each other. So I think that conjecture must have some substance because it includes this non-trivial special case. So yeah.
Roger, is there so this, I mean, as Aubert said, this feels at a naive level some kind of, you decompose the right-hand side of Baum-Cohn, and for individual pieces you're attaching some topological spaces, and the K theory should match the K theory of the individual piece. Does these spaces, this compact circle you were just talking about, do they assemble to something? Are they parts of some kind of related to the left-hand side of, maybe not Baum-Cohn, so that's K homology?
I think ultimately this is independent of Baum-Cohn, actually. Yeah. This is an independent conjecture. Yeah.
Would one imply the other in some sense? Are they ways to go from one to the other?
I think, I'm not sure, but I think this may be, first of all, the Baum-Cohn conjecture of p-adic groups is pretty useless because the left-hand side is uncomputable. So elliptic operators on Euclidean buildings and all that. So the best you can do is replace the left-hand side by something else. That's a long story. So perhaps in that context, you can say that the right-hand side here is a nice substitute for the left-hand side of the Baum-Cohn conjecture in this special case. But it is independent of the Baum-Cohn conjecture.
Yes, but it feels like you have this.
In a way, it's a more precise. You could say it's a rather more precise version. If it's a version of the Baum-Cohn conjecture at all, then it has more precision. Yeah.
In some sense, if we understand how to use the amalgamate map to go from this side to the other side, you could maybe understand better the other side.
Mm-hmm.
And from the other side, we have tried to look at it using a chamber homology, as Roger said at the beginning.
Yes.
Mm-hmm. So the right-hand side essentially is something that you only get to after decomposing the group, the C-star algebra. Then these spaces appear. So globally, you don't see that first as a left-hand side, computable left-hand side. You only see it after the decomposing to pieces. These
that's right.
things.
I think that's right.
Maybe there is a way to also decompose the left-hand side into pieces. And then in that case, it would be a refinement of Baum-Cohn conjecture. Saying that each piece, it will be a kind of Baum-Cohn conjecture for each S. But for that, we need to understand how to decompose the left-hand side. This is
I mean, in Baum-Cohn, in the you know, if you have a nice, if the space is nice closed spin manifold, you know, this whole, you can avoid the K homology and operators by say taking Poincare dual and just do topology, topological K theory. But of course, in the, I guess in Euclidean buildings, you don't have that Poincare duality necessarily. I don't know what there's a topological version for the left-hand side that you could use. This seems to be something like that, that could just topological K theory. Any other questions or comments? All right, and let's thank our speaker and all our speakers actually. Thank you very much for your hard work. I realized actually after watching through all the lectures that what we asked after the lectures is quite ambitious. So quite packed lectures. So thank you very much for preparing all that. Right, so I should stop the